All right, then. Hello, everyone. My name is Marcin Jasiukowicz. I was a student in the EMSS program a year ago, rather in the previous pilot run. I was just finishing up the semester in Bremen exactly a year ago, as you are doing right now. And I was thinking that maybe I can give you an update what I'm doing exactly a year later. And so it happens that over the course of last year, actually already in December last year, last year I mean 2022. So um, I applied for a position within the European Space Agency. It was an internship position, so not a young graduate position, but just an internship. I applied while I was still in Bremen, and about December I got the position. And my planned date to start was August 2023. I started on the 1st of August, and right now it's 6 months later, and it's basically the end of my internship. I will be finishing in about a month, in about a week. So with that said, I wanted to show you what I was doing throughout the last 6 months, and also give you an update on what I'm doing regarding my master's thesis. So the scope of the presentation is to show you what is OPSAT. This is the project I'm working on. I'm a mission control engineer in the OPSAT satellite mission control team. And I will kind of talk about the technical makeup of the OPSAT mission, the space segment, which is the stuff which flies in space, the ground segment, which is some of the stuff that surrounds me in this room, but also some of the antennas around Darmstadt and in other places. I'll talk to you about the sort of a system split of the mission, how the systems interact with each other, and how they make a mission together. I will show you how part of my job, which is operations of the spacecraft, what do we do in order to make the spacecraft do the right thing at the right time. I'll provide you with some updates on the mission, and then I will cover my master thesis, what I'm focusing on especially. So yeah, OPSAT Space Laboratory, it is a CubeSat, which is meant to be a powerful, flexible, reconfigurable satellite in space. It is a CubeSat, 3-unit CubeSat. I will show you a picture of it later from up close. And it's supposed to be a platform for people to run their own experiments on. So the satellite has already been sent to space. And it has on board several subsystems which people can come and use for their own purpose. And each of the missions within the OPSAT Space Laboratory has a theme. OPSAT 1, which is the current mission, was focused on communication protocols. That means that it has several subsystems related to communication. Radio frequency communication in different bands, but also beginning of light communication tests. And the next OPSAT mission, which is going to launch about in 2025, is going to be focused on optical and quantum communication, so fully on light communication. So this way, once the mission is sent, people can, without deploying their own hardware, without launching their own satellite, they can use our platform and they can run tests without incurring any additional costs. And this platform is open for all European industry, but also universities. You could apply for an experiment or onboard OPSAT if you wanted to. So maybe that's an idea for a master thesis for you. Although I must say that the mission is coming to an end really soon, but I will cover it in a moment. Yeah, so you can see the picture of OPSAT. It is a 3-unit CubeSat. It is called, people here internally say that it's the only satellite which is actually owned by ESA because it was fully paid by ESA money. and it is fully operated in-house. Some of the other missions are usually paid by external sources like European Union or particular governments, but this one was fully developed within ESA to also improve the operational knowledge within ESA. And here right now I'm in the European Space Operations Center, which deployed the satellite and is operating it on the daily basis. So since the mission has launched in 2019, we just celebrated its fourth birthday just recently in December, and since then we have deployed over 271 experiments from 26 countries on board of OPSAT. So I want to talk a bit about what we actually have inside of OPSAT. This is the shoebox-sized satellite. It's 3 units, which means it's comprised of its dimensions are basically like 3 10 by 10 by 10 cubes. So it's 30 by 10 by 10 centimeters, and inside you have the following components. The satellite is split into sort of a satellite bus or a platform and an experimental part, which is used by experimenters. And on top of that, some of the components are double redundant. So technically inside we have 2 or 4 satellites, however you want to count. So some of the components are redundant, and they also overlap in function. So the satellite bus is what we have complete control over. It has an Nanomind computer, which is like safe software, which we don't really modify. And again, there are 2 of them. So even if we update the software, we always only update one, and we can always fail over to the other one. And it has 2 means of communication using UHF ham radio bands and S-band antenna, which I will talk about a bit later. It also has a ADCS system. ADCS stands for Attitude Determination and Control System. We call it the coarse ADCS because it only includes magnetometers, magnetometers, photodiodes, and gyroscope. So it knows its position, and the only way it can control the attitude is using magnetometers. So it's not really accurate. It's just meant to de-spin the satellite in safe mode, so it's not spinning up, and it doesn't destroy itself. Then we have the payload experiment, and here we have some more powerful hardware meant to play around with and experiment. And the heart of the experimental platform is a satellite experimental processing platform, which we call SEP, and it consists of a FPGA chip, ARM CPU with 1 GB of RAM memory, and some additional memory also. So it is a system on a chip with an FPGA and a CPU and some additional memory. So basically, you have a quite powerful Linux computer on board. It runs Linux, so you can run standard software on it. You can program in Python. People also deploy Java on it. So yeah, it's enough to run those. But also, if there is a specific use case, people can deploy their firmware on the FPGA module. The FPGA module is also connected to all the following subsystems, so people can sort of mix and match the signals and introduce novel functionalities to the platform. Then there is another component which is especially interesting to me. This is the software-defined radio. It only allows you to listen, but it's you can listen. You have basically a radio in space which you can tune to any frequency and listen what is on that frequency, and it's really useful, really cool because you can. I call it taking radio pictures over the Earth. You can do a short recording over some spot on Earth and see what is going on there in radio waves. There is also GPS receiver, although it's not currently working. Speaking of pictures, there is a HD camera which is facing to the bottom of the spacecraft, and previously mentioned optical receiver, which there were attempts at laser communications with it. And then I already covered the coarse ADCS system, but we also have a fine ADCS system with with a more accurate measurement devices, but also more accurate control in namely reaction wheels and some more magnetometers. Reaction wheels allow you to actually do accurate pointing, which matters, for example, for the HD camera. We can actually do pointing towards the ground, pointing towards the stars, and actually get more or less accurate pictures. On top of that, there is also an X-band transmitter, very much in the topic of communication. So it allows for a higher data rate with Earth, although it has not been used in a while, but it's also an option. Yeah, here I wanted to provide a bit of a system layout. It's not entirely visible probably on your screen, but the main thing is we have the payload, rather the satellite bus up top, which has a motherboard with 2 nanomines, which are redundant. And then we have sort of on the left the communication part with the optical receiver at the very bottom, CCSDS engine, which sort of implements the space protocol to communicate with the satellite, and this engine is connected to a bunch of connectivity methods, to the X-band radio, to the S-band radio, and it can also be switched over or bypassed. Then we have also the SDR, which is kind of a passive method to just listen to the frequencies. We have the fine ADCS system and the 2 step computers on the right, as well as the HD camera on the bottom. And some spaghetti in between, which tells you a bit more how it's connected. If you're interested, I can show you later where to find this graph, and you can get more about it. Right in this room where I am, so we already covered the space segment, which is already in space. It's been launched in 2019 and it's flying ever since, and we basically cannot touch it. But if you want to debug the hardware and see what is going on, how we can maybe fix some problems, we also have a copy of the satellite on ground, and we call it a FlatSat. It's right here on the left besides me. You can see the picture of it here, and basically it is the same satellite, but it's spread out on a table. That's why you call it a FlatSat, and it's basically an exact copy of the satellite in terms of hardware. It's missing some of the components, like the solar panels, which are simulated using a laboratory supply, but it gets the job done, and you can deploy the software on it the same way as you would do in space, and you can see before the deployment how it will react, and then verify it in space. You will know that it will not crash the spacecraft, and you can safely execute the same experiment in space. Yeah, we also use it for debugging. So we've seen some degradation of the components in space, and then we can test our assumptions and do some debugging on ground, see how we can fix those issues, see how we can maybe deploy software patches, how we can reconfigure the spacecraft to fix those issues. And it's been really useful throughout the last years to the mission control team. So right now I wanted to talk to you a bit about the orbit of the spacecraft. I wanted to show you a simulation of how does it look like. For me, I'm a kind of like a visual person, so I like pictures. I like to actually experience how the stuff works before, like the description doesn't really work for me. I'm sure it might be similar for you. So I will show you a bit of a map here. And we can also discuss about the end of the mission, what is exactly going on, which makes the mission end soon. So right now I will switch over to a screen I prepared before. And now we can see VTS time-lapse software, which we use for operations. And here I have loaded the position of the satellite in time, and also some attitudes data. So we can see in the recent days how the satellite was actually positioned in space and what it was doing. So first of all, I wanted to show you exactly what it means that the satellite is in a sun-synchronous down-dusk orbit. So you can see here, the satellite is more or less flying from north to south in every orbit. And when I move the time around, you can see that it always overflies over the sunset and sunrise of every day. Yeah. So it does a revolution every 90 minutes, and every 90 minutes it crosses the line where there is a sunset and a sunrise. What it means practically that the satellite is sort of glued to the inertial space in the galactic, or rather in the Earth-Sun system, and it will be always pointing towards the sun. Right now, you cannot really see much movement. The sun moves, but also the orbit rotates ever so slightly following the sun. So basically, this is what it means that the orbit is sun-synchronous. It's locked to the sun. And in our particular case, you might have heard about sun-synchronous orbits, which are shifted by 90 degrees, and then they would always overfly the part in the middle of the day and over midnight. In our case, we are shifted by 90 degrees, and we always cross the sunset and sunrise part of the Earth. So yes, before I move on, I will briefly cover the next topic, which is the orbit degradation. So the satellite was launched in 2019 to a 500 kilometer orbits, and since then it has been lowering quite quick. And this is partly caused by induced drag due to higher solar activity. So because the solar activity is higher, the atmosphere is a bit more perturbed, and it sort of grows in size. So the atmosphere reaches higher altitudes, and this is what causes the spacecraft to lose altitude because it encounters higher drag, and the higher drag slows it down, and because of the reactive gravitational field, the orbit gradually lowers. And it's been especially bad in the recent months. So since the beginning of my internship, which was in August, we lost about 20 to 30 kilometers of altitude, and it's only falling slower. So to remedy that, what we are doing throughout the last few months is we introduced what we call horizontal pointing. So usually we kept the spacecraft either in nadir pointing, meaning it was pointing with the camera to the ground. This allowed us to take pictures and to imaging experiments. But as you can see, due to the construction of the satellite and the big solar panels it has, it also introduces a lot of drag. So in order to reduce this drag, we introduced a procedure we called horizontal pointing, and we just shift the spacecraft by 90 degrees. And this way, the spacecraft is pointing with a smaller area towards the vector of light. And this minimizes a bit of the losses due to drag, and allows us to expand the mission type just ever so slightly and just squeeze out a little bit more science out of it. So coming back to my simulation, now perhaps you will know what to focus on. If I switch to the view with the satellites, you can see the Earth down here. You can see the sort of the orbit of the satellite, and here in front you can see the cone of the camera, which is looking forward in the direction of light. If I now start the simulation, you will see that the spacecraft will always keep parallel to Earth. Sometimes it does a little bit of a dance to detangle and desaturate the reaction wheels inside. It cannot just keep its attitude forever, but for most of the orbital time, it just keeps in this attitude. So this is what we've been doing for several months now, and a few months actually. And this allowed us to expand the mission time, but several weeks, few months. Without it, we would probably be re-entering now. And thanks to this procedure, we got another few lives. And right now, the time to the orbit is about August this year. So still some time. And this also shows you that you need to be quick if you want to do some experiments of OPSAT, because it will soon cease to exist. So now I can move on and cover even more of the ground segments. So I'm going to speed up a bit. I'm not going to go into too much details. So the ground segment, the ground environment here focuses on this very room I'm in, which is SMILE. SMILE stands for Small Mission Infrastructure Laboratory and Laboratory Environment. And here you have all the building blocks to make the mission work. So here, right behind me, I hope you can see it, is a server rack which is connected to one of the antennas here, and it serves as a proxy to communicate with the satellites. So that we have one shoebox sized satellite in space, and then we have a rack of hardware here, which is directly, well, not directly connected to it, but facilitates communications with it. And to facilitate the contact, we have three antennas. One is ESOC1, which is outside of the building under this dome. Inside is a parabolic S-band antenna. And just over my head on the roof of this building, we have a UHF VHF antenna like this. And in another location in TU Graz in Austria, which is the university who actually built the satellites, they have another antenna. So the S-band antenna, you can see a typical spectrum of rather graph of strength of the signal over time, but hopefully you will see it in about 20 to 30 minutes when we have an actual pass. And I just wanted to highlight that on board of the satellite, we have a patch antenna, two patch antennas on both sides, and we have the corresponding S-band antenna on ground. In this graph, you can see an interesting phenomenon. When the satellite is overflying Darmstadt, you could imagine it flies over your head. And here, where we lost the signal briefly, is the moment we switch over from one antenna to the other antenna. So we lose the signal briefly for a second, but then it comes back up, and the antenna follows it along. So yeah, the same subsystem is actually responsible for two of the communication bands, so S-band and X-band. And the usual speed that it allows us to communicate with the satellite is 256 kilobytes up and 1 megabit per second down of data rates. And using the X-band subsystem, we can go up to 50 megabits per second down. So it's quite fast. It's not the fastest thing in the world. There is also some overhead there. It's not just the speed. There is also the latency of the connection. But it's quite performant, and it allows us to exchange farabits of information between the satellites. Then we have also the UHF segment. This is also worth to mention. We use both of those antenna systems, the UHF one and the S-band, are sort of double redundant. So we call it two operational chains. There is a chain using S-band and B chain using the UHF. And if one of them fails over, we can keep communicating with the satellite and send commands to it using the other one. But the UHF one it's much slower. It works up to 10 kilobits of data rate, so it's really slow. It allows us to send only really simple commands, and usually we don't even get a reply back. But it's always nice to have, and it allows us to always have this additional way to recover the spacecraft. It uses two antennas up top of the satellite, just two dipole antennas, and there's also some issues with the noise. As you can see, we had a test done some years ago flying over Europe. You can see there is much elevated noise floor for the satellite, for the UHF frequency band, just because there is a lot of stuff actually working in the 437 megahertz range, the 70 centimeter radio range. That shows you that it's not perfect, but still nice to have. What is so nice about it, that it works in the 70 centimeter range, is that we can actually cooperate with ham radio operators from all over the world. And the data and the formats in which the satellite is sending data out is public, and people can set up their own ground stations. There is actually also software provided by us, which allows people to decode the beacons that the satellite is sending. And you can, people who receive the packets are usually from a project called SatNox. I totally welcome you to get familiar with this project. It allows you, even yourself, to build a custom satellite receiving station. and it acts as a network. So the network provides the tracking information for any particular satellite, and then your antenna will move in unison with some other antennas, and it will record the signal as it's coming from the spacecraft. The project is maintained by Libre Space Foundation from Athens, Greece, and I invite you to get familiar with it. This is definitely one of the highlights of the mission. And here we can see a bit of the software people could deploy. The software we provide is this application beacon monitoring on the right. You can download it from our GitHub page at github.com/esa/gr-opsat. And this is the actual setup we have right here. You can also see there is a monitor right beside me with the live view of this antenna. You can see it in the picture here. And also additional stuff that people cannot do, but we have additional software to do so. We have a simple terminal communication with the spacecraft, and we can send basic commands to it. And if you remember the previous section about the makeup of the satellite, we can communicate directly with the onboard computer with the satellite bus, so we can recover it. And it was also used for provisioning right after launch. So now I would like to move to another topic, which is the daily operations. And this is like the bread and butter of what we do here at the European Space Operations Center. This is what I have been mostly involved with throughout the last 6 months. And what I want to show you here, I call it the three horsemen of the apocalypse, just because of how it looks like, how it acts, and how we typically work with it. So on the bottom left or bottom right, you can see sort of the V software to communicate with spacecraft. It is a standard within the European Space Agency. It's been developed in-house throughout the last several years. It's called SCOS 2000, and the first version of it appeared in the year 2000. But it has been updated ever since. Right now, there is a next generation of the ground segment software, but because the mission was launched a couple of years ago, this is what we still use. And it's it might look harsh, but it's a really dependable piece of software which runs everyday operations, not only of OPSAT, but also of other missions. So actually, I can come to another live demo. I can show you an actual virtual machine we use for operations. I will also show it to you in a bit when we actually going to have the satellite pass. But this is basically what we have. We have several windows. Application manager, which allows us to open up some applets, and what is mostly interested to us is telemetry history, telemetry packet history. This is all the telemetry packets we receive from the spacecraft. Right now, there are no packets because we are not actively tracking the satellite. Oh, actually, you know what? I'm connected to the EM, so don't worry. Right now, it shows that we have signal, but yeah, it's. I'm gonna show you the real thing later. So here we have, we see the telemetry packets coming in this case from the engineering model, but later you will see actual packets coming from the spacecraft. We also have telecommand history here. So this is all of the commands we send to the spacecraft. And on the right, you can see the status of those commands. If they are green, it means the spacecraft has received them. If it's anything but green, it means there is some sort of a problem, with red being total failure. And we also have manual stack, which allows us to send commands. There is a predefined list of commands which is implemented on board of the spacecraft and in the ground segment software, and we can find any particular command, put parameters to it, and then send it out to a spacecraft. Either at a particular time or using the two buttons here, arm and go, we can actually send the individual commands. We also have a helper telemetry desktop. And this is what's really interesting to me, because you can clearly see that it's been inspired by some of the old systems. And it's clear to me that it's been inspired by like the systems that were developed here since the 70s, since the beginning of the space exploration and European Space Agency. And they just kind of carried over some of the visual aesthetic, like the green letters and black background from like CRT screens. And this is sort of what we are still working on. But as you can see, in this software, we have only the ability to send particular commands, particular packets. Yeah? And the characteristic with OPSAT is that we don't really have much time in a given pass, as you maybe will see in a moment. So we need to be really fast. And it's really not feasible for us to send the packet by the manual stack. And just like it would not be feasible. We cannot possibly send them fast enough. Although it was done at the beginning of the mission when we are doing the provisioning, but that was a much slower process. It unfolded over a week of operations, and people were preparing and verifying the manual stack. They were sending one at a time, verifying the proper execution in the next passes. So it was safe and steady. But right now, with a lot of experiments going on, we need a bit more of efficiency. So talking a bit about the historical heritage, what used to be going on and what is still going on some of the other missions, you usually have paper procedures. And the paper procedures, you have a title of a procedure, it has its identifying code, and it has its name, description, and then it has a list of steps you need to introduce, you need to execute in order to reach some desirable outcome. And usually some would get a person called Spacecom would receive such a procedure, and based on this procedure, they would prepare appropriate manual stack, and then they would send the commands basically manually. So the next piece of software we have on the mission is Mattis. It is much more modern software. It's been developed in about the 2010s, so it's a bit younger than SCOS 2000, and this allows you to predefine sets of operations right here in the software. So if I were to show you, like, for example, here we have a script to start experiment, and here we have a almost pseudocode like a way to structure the procedure. So what's previously used to be steps on a paper right now are a piece of code. It's not exactly a programming language. It allows you to do basic flow control, ifs and functions and data queries and such. But it's not really meant to be a programming language. It's really meant to be an explicit way to describe a procedure from start to finish. So it's easy for ground operators to prepare and understand and execute. So you would take any kind of procedure, you would write it using the pseudocode, and then it is available in the software. And then it's much simpler because you're not sending the individual commands. Right now, you're abstracted away a level higher, and you can just click a particular procedure. In this case, I can start an experiment. I can type in a number for what experiments I want to run. I can send the command to the spacecraft, and the spacecraft will confirm the reception of all of the underlying commands. And then the software will report the execution of the entire procedure. But it's still not kind of quick enough, because this we could do during a live pass, but any given pass of OPSAT over Darmstadt takes about 6 to 8 minutes. And still, we wouldn't be able to run all of the commands, especially that we do time tag commands. So we not only send the commands at a particular moment right now, but we usually do scheduling for the next 2 days into the future. And this is where I'm going to surprise you. For the day-to-day operations here in European Space Agency in the year 2024, we use Excel. Excel runs the world, not only the financial systems, but apparently also space systems. And yeah, my skills with Excel have improved a lot. So yeah, if you don't know Excel, you don't learn it. You're gonna learn it on the job. So basically, what we have right here, it is a way to prepare the command for later execution. So we have each line in this file has the procedure name, the time of execution, the time it's going to take, and then we have some parameters we want to include in this procedure. So basically the same what I would do here by clicking manually and inputting the values myself. But now they are specified in the Excel file, line by line. Also, we have a helper. We have already predefined sets of procedures we need to run in order to get a particular outcome. For example, run an experiment. And for example, For example, let's take a camera experiment. If you want to take a picture of um, of Earth, we need to first stop the procedure, which is keeping us in the horizontal pointing. Then we're gonna start a procedure which is turning us to nadir pointing. Then we are gonna start a procedure which tunes on the camera, so gives power to the camera. And then at the end, we're gonna tell the experimental computer to start an experiment, which is actually gonna take the picture, and then do the same process but in reverse. So turn off the camera, stop nadir pointing, stop starts horizontal pointing, and carry on with the mission. And in any given 2-day schedule, we can run from just one to a dozen experiments at different times of day, at different times of in orbit. So this is also where this software comes in useful, because we can actually find a good spot, for example, for a picture where there is a daylight and it's crossing a particular region of Earth. And we can find those times, put them in Excel, and execute a particular experiment. For example, here to take a picture of over South America. So yeah, this is basically the daily operations of the mission. And yeah, today we actually are preparing a recovery schedule, because we need to reset the system. We had some anomaly which caused the onboard computer to reboot. And in 15 minutes, we'll have a pass. I will try to show you what we are going to do. So let me carry over with the presentation. I should not have much more content left. Right now, I will come to the experiments. So yeah, here we can see a bit of the pictures that have been taken by the OPSET mission. I myself also managed to take a picture myself, which is a really great experience. It was within the first month on the job. I managed to do several schedules for the spacecraft. I was responsible for the daily operations of the satellite, to send the right commands to it. And the perk of the job was that I could schedule my own experiment. And I thought that why not? I would take a picture. Sadly, I was trying to get a picture of, like, I don't know, either Gdańsk University of Technology or Hochschule Bremen. But it was too late in the year, and at this time already we went into winter, and at winter time on this orbit, when the satellite flies over, right now, as you can see, it's already dark outside, so I cannot really take a good picture of Earth. But I had got some amazing pictures of New Zealand. It's actually not here, but maybe I'll show it to you later. So yeah, there are some mission status. I'm gonna just skip to what I'm doing in the second part of my internship. So about since November, I focused in my master thesis on the software-defined subsystem of the satellite, and I wanted to fix a particular problem we are experiencing regarding data handling. So as I've mentioned, there has been some degradation on the mission. So from the original experimental platform, in which we had two subcomputers, the experimental computers, the two Linux boards, only one works. One broke shortly after launch. And then even then, in this one board which works, we have further degradation. So out of the two cores in the CPU, only one works. And also there has been some issue with writing to external memory. And we cannot really use the full memory which is available, at least not directly. We need to use a particular workaround. So on the left, I will explain to you how particular SDR recording works. And just as a bit of a background, SDR recording produces a lot of data. It is you have basically an electronic subsystem which samples basically a piece of wire at really high frequency, and it's just a lot of values. You might know the sampling law. And if you wanna reconstruct a given frequency, the sampling rate needs to be twice as high, and the frequencies we are looking for are about 400, 500 megahertz. So yeah, we are using using way higher sampling frequency to actually recognize those frequencies. And because it produces a lot of data, and because our memory is quite constrained, in turn we can do really short recordings from the SDR subsystem. So when I joined, it was 2 seconds at the lowest sampling rate. Shortly after, we could go to 30 seconds. But now I'm working on a method which would allow us to go either indefinitely or quite high in the gigabytes. So for going from 30 seconds to maybe even 3 to 5 minutes of recording time on orbits. Still not infinite amounts, but definitely better than 2 seconds in the beginning. So how the problem is laid out is basically we have the SDR subsystem, we have the antenna on the left, we have the SDR subsystem which feeds to the FPGA. The FPGA does some basic firmware, some basic processing of the samples, and then they are forwarded to the experimental computer. And sadly, the file system of the experimental computer is only limited to 100 megabytes due to the degradation. But we have another connection to a external memory chip, which is part of the FPGA. It's literally a memory chip which we can communicate directly with and write and read to it. But we can do basic read and write binary operations. So the recording time is always constrained by the 100 megabytes because we can save it to the file system, and only then we can pass it on to the external memory. And then we downlink the signal. But what I was trying to fix in my master thesis, in the work of my master thesis in the last 3 months, was to modify the SEP side, the experimental computer software side, to allow for direct writes to the external memory. So we totally skipped the limitation of 100 megabytes, and you write directly to the partition, which can be bigger because the chip we have is 16 gigabytes, and we could possibly create a partition that reserves a particular size, maybe 2 gigabytes of memory, and then we can fill this memory without any sort of constraint. But there comes another issue. If we use if we generate this much information, it's really hard to downlink it to Earth because we only have 1 megabit connection. So for a 30-second recording, we can do right now. It weighs about 100 megabytes on board of the spacecraft, and without any further processing, it takes us about 2 days to download those samples. Again, it's not too bad, but it's constraining other abilities. It constrains the amount of other experiments we can run, and do mind that the mission is coming to an end. So we really want to increase the pace of doing experiments and squeeze out the most science coming to the end of the mission. So then comes the post-processing part. First is generating a waterfall, which is sort of an image like this. This shows you all the frequencies that have been recorded on board of the spacecraft. In this particular case, this is a sample recording I did with my friends when I was in Hamburg just 3 weeks ago. On the ground side, I was standing with an antenna and a ham radio, and I was transmitting a signal to the spacecraft. And on board of the spacecraft, we scheduled the recording at the right time, and we were trying to communicate with it. We sent some New Year's wishes to the satellite, and the satellite heard it and captured the samples. You can see part of our transmission here in the middle, but you can also hear another stuff. And as you can see, it's a lot of data. It's a really wide SDR, and our transmission is just this one bit in the middle. So here comes an assumption, like we don't really need to downlink everything. And the logic is that we can first download an image like this. We can see what was recorded on the spacecraft. We can do the basic processing, and such an image weighs about 8 megabytes. So it's much, much, much better than the 100 megabytes before. So we can then download this 8 megabyte recording to ground. Then as an operator, I can look at the picture. I can make a decision. Okay, taking into account the frequency we transmitted on, the Doppler shift, and all the other like the other frequencies you can see, I can make a decision that this is the recording that I want to download, and then we can send this information back to the spacecraft, and then the spacecraft can cut up the recording out of the big file, out of the 2 GB file we have stored on board. We can just cut out the bit we want. So it's being cut out in 2 dimensions in the time domain. So we only get a few samples in the middle from the recording, but also in the frequency domain. We resample the recording to go from wideband, from all those frequencies, to just this one middle frequency. And then the results should be quite a short file, quite a small file, which can safely be saved within the 100 MB limits of the main onboard computer. So we kind of do a trade-off between the memory and computing time. So we introduce a bit more of computing time. We crunch some numbers, and instead we get a smaller file. And then the smaller file, maybe with this increased recording ability, maybe it still will weigh 100 megabytes, but it will cover a much longer recording time. It could be a 5-minute recording for what it's worth, yeah? Or we could do still a 30-second recording, and then it would downlink in just 1 pass or 2 passes instead of 2 days. So yeah, I'm about midway in this project. I got the first part, which is the saving to the external memory, pinned down right now. As you might notice, I'm at the end of my internship, so I'll not be able to work on this project anymore as the mission control member, but I can still continue working as a outside experimenter, and this is what I will be doing over the next few months. I will be contributing externally. I will be providing updated versions of the experiment to the mission control team, and the mission control team will run the code for me. So yeah, this is the state of my masterpieces. Now I will close off the presentation by just mentioning some of the other stuff we have going on board. We did, as I mentioned, apart from taking pictures of ground, we can also take pictures of sky. We took some pictures of moon, for example. There is a lot of software experiments I could not possibly cover, but like sort of the most the easiest to understand and the most showing of the capabilities of OPSAT is the chess experiment. You can go right now to the website chess-ops.space, and there you will see chessboards with some pieces. And in every pass of OPSAT, we get a move from this website, which picks the most popular chess move out of all casted votes. And it takes this move, it sends it to the spacecraft, and onboard spacecraft will have a chess engine, which runs briefly for a few seconds. It tries to come up with the best answer to that move, and it gets sent back to Earth, and it gets updated on the chessboard. I'm not sure if we have started a new game. I think last of the game ended up in a defeat from the side of OPSAT. OPSAT defeated Earth, but last year we had one game in which we've won. So currently the match between space and Earth is 1-1. Let's see how many more games we can win until the end of the mission. So basically we come to an end. Here you can see a bunch of links with some additional supporting materials. One I want to highlight the most is the community platform for experimenter. Please go to opsat1.esoc.esa.int website. This one will point you to all the relevant materials, the current state of the project. And if you want to, you can also log in on this website, create an account on this website, and write us an email or write a proposal for an experiment to run on board. And the mission control team will read your email. They will see what can be done, and they will support the execution of your experiment on board. Also worthy of note, at the very end, you have some images taken by OPSAT. And this brings us perfectly to a close, because just in 3 minutes, the satellite is going to fly over Darmstadt. So I'm just going to close the presentation and briefly set up the environment. I will quickly show you the current position of the satellite. So as you can see, on the map here, this is a simulation. This is not live information, naturally, but the satellite is just oncoming. It's not technically flying over Darmstadt. It's flying over Russia, Belarus, and Ukraine. but we can see it comes into the field of view of the antenna here in Darmstadt, but just a small margin. So it's just gonna pop up above the horizon, and we're gonna see a bit of telemetry, and probably that's gonna be it. So I'm gonna keep that window open somewhere in the background. I'm gonna switch over to the main operational chain. So not the dev one connected to the engineering model over here, but to an actual one connected to the antenna outside. And I will also show you the graph of the antenna position here. So let me quickly go to the default view. So here on this graph, you can see that the antenna is starting sort of a calibration dance, and in a moment you will see those two numbers increase. One number is the elevation to the one number to look for, excuse me, on the ground. Currently, the antenna is pointing towards 3 degrees above the horizon, but it will soon go up to 7 degrees. And thing worthy of note is that the antenna is only enabled above 5 degrees. So once it clears the surrounding buildings, only then we can use the antenna to communicate with. So out of the 7 degree pass, we only gonna have literally 2 degree pass above the 5 degree threshold. And then you can also see the azimuth on the left, which is basically the position of the antenna. 0 is the north, and then I believe the antenna should be following the sky in the east. So it should be a positive number towards the right. Yeah, and down below we will also see the spectrum, the signal strength of the satellite. Once the signal gets powerful enough, and once the antenna will be pointing above 5 degrees, we will have ability to do two-way communications. Otherwise, we only get telemetry from the spacecraft. And here we have the operational chain already opened, and I believe we have just loaded a new schedule. So if I click here, we're going to have a list of operations. It's a bit slow because it's actually thinking, but here will be a list. Some other team member today prepared a list of commands which are going to be sent to the spacecraft, and yeah, they will be sent out to the spacecraft once we get a little bit of signal. Most likely, most of the schedule will be sent in the next pass, which is going to be a nice 90-degree pass. I can show it to you in the software. So the next pass should be in about 90 minutes. And so in about 90 minutes, the satellite's going to make another rotation, and you can see that it will fly over that center over Darmstadt. And actually, not too far off from Bremen. So maybe say hi, maybe wave to it. I can show you an application which will allow you to track the satellite. It's an app for your phone you can actually use, and it shows you the position of the satellite in space. So you can try to sort of follow along with your phone where the satellite is, and maybe wave to it. So yeah, here you can see the list of commands. And at the moment now, if we get BitLock, so right here on the screen on the left, we see that we are now getting telemetry from we have a telemetry link. Let me actually verify. Not yet. Let's see where we are. Yeah, see, the antenna has just started tracking. It's just elevating, just moving up. And we should see some signals soon. We'll see if it happens. There might be some additional manual things to be done in order to see the signal. Just as I mentioned, we experienced a reboot on the spacecraft, so it might not be in the default state to see the commands. But maybe we'll see in a moment my friends actually sending a command using this chain here. So yeah, I'm just gonna play the simulation in the background. So, whoops, that's too fast. That's not real time. it is a simulation, but I can align it with the real time and see where the spacecraft actually is. So as you can see, it's just coming into the view of antenna. I'll put it side by side with the graph. So as you can see, well, actually, it seems that the antenna is already pointing about 5 degrees. So the simulation may be a bit late, and we are waiting for the signal to appear. Yeah, we still do not see telemetry. I will open up. So this is the A chain, but there might be some action going on the B chain. We'll see if that's true. So the B chain is the backup chain. If the main chain is not working, if we don't get enough signal, then there might be some operation in the B chain. Usually at this time, I would be joining a meeting with the team, so I would know the updates as they go. I could help along, but I will do it for the next pass. This pass is more of a dry run. Actually, I think that people just skip this pass because nothing's going on. Literally, no one's doing anything. So yeah, I'm not gonna touch it. But yeah, we already muted, so I believe shortly the antenna will go below 5 degrees and will lose commanding ability. So nothing much happened in this pass. It was really just a demo of what is actually going on, how the windows look. In this pass, we never got the signal from the spacecraft, so this is what we will be doing in the next pass. Try to upload the schedule and do some of the operations. So with that said, I think I can start going to questions.
Thanks for the presentation, Marcin. Quite informative.
Thank you.
One thing I was thinking, you just said that you're probably will be joining the next run. Was how is the whole how are you working? Do you work in shifts, or how does, because normally you wouldn't be in office in a normal day job.
Coming back to your question, you asked about the sort of day-to-day operations. It's a good question. So how we do it usually, we start about like, just because the classes are 12 hours apart, you cannot like fit two into one shift. Yeah. So we usually start in a given day around 11. At 11:30, we have a team meeting. After the team meeting, we usually have eat lunch and discuss what we are going to do on a given day, and then we have a period of work between about 12:30 1 p.m. to the first pass, which is about 6 p.m. And then, yeah, this is the first opportunity we can actually, I call it like a Schrödinger box. Like we prepared for something, we discussed something based on an outcome from the morning passes. But then in the evening, we get another peek at the box, and so we get updated situational awareness of what is going on. And everything is well, we proceed with the plan. Everything gets sent out. We upload new schedule. We get the results from the satellite. But if something goes wrong, this is the really hard part because it's already evening. Yeah, it's already basically normal. Everyone's left from here. Yeah. Yeah, we then sometimes have to do some hard operational decisions and maybe recover the spacecraft, do some hard thinking to actually figure out what is going on. And then we have maybe, so between now and the next 90 minutes, we have a chance to maybe change some of the plans, prepare some manual operations, and then that will execute in the next pass. And then sometimes we would have another pass, which is like 9 p.m. already. Yeah. So this time you either skip the last pass or maybe you manage it, but then it makes sense to start the next day about 11 in the morning. But sometimes some of the people here have to wake up in the early morning. Some people were really brave about it, and they start like 6 in the morning, just wake up, look at the laptop, see what's going on. But this is perhaps the thing that I have not highlighted yet. The perk of the job is that it's totally sort of virtualized. Yeah, so one of the server racks behind me was a server with just hosting all the infrastructure. And we can do it from the comfort of your home. Sometimes you have to also do it on the weekends. This is something I've learned that was really new to me. You would not perhaps consider it, but yeah, the satellite doesn't stop. It doesn't go away. It's just like the sun. It's always there. It's just on the other side of the earth. So it also flies on weekends, and sometimes you also need to do the operations on the weekends. Myself, I didn't do it. I really kept this time to myself. But the people that are actually employed here, they do it in the morning classes. Of course, we do not do anything crazy. We just do just maintain the operations. It's more about the situational awareness. So we just open the laptop just to know what is going on. If something really critical is going on, you put the spacecraft in a safe state, which can survive through to the week. And then we're gonna actually figure out what's going on and then and do the actual corrective actions. Yeah. But yeah, it's sort of a constant job, and after 6 months here, I feel I'm a slave to the machine. Yeah, the machine's flying. It has its humor. It tries to just the other week, like on Friday, it decided to reboot. Like just within last week, I think we had just 3 reboots, and one is on Friday. And like my entire week's work, I was prepared to run something over the weekend and come on Monday, have some experimental results. And the satellite just decided, no, not today, not this week. We're gonna cancel that. Yeah, but this is very much characteristic, in particular of this mission, and in particular this late into it. So after 4 years, seeing this degradation, some of the other. So as I've also mentioned in the presentation, all the missions are much less paced. So they are not this sort of quick iterative process. You usually go slow and steady, and the missions like imagine a mission flying around the sun. Yeah, like we have Solar Orbiter, for example, here. The mission is planned for years. It was launched like already a few years ago. It was planned for the last 10 to 20 years, and then it's going to be in operation for the next 10 to maybe 20 years. I'm not sure exactly what is the time frame of that. Yeah, so they kind of work slowly and more methodically. And also the important thing to note, all of the big missions here at ESA have the support of the S-track system. So of the antennas all around the globe, high gain antennas, big antennas the size of a huge building, and then I can actually track the spacecraft deep in space for hours on end, and then you have hours-long communication window. And this is also the point which I mentioned. You can actually have the procedures and execute them slowly, methodically, command by command. But it doesn't work for offset, especially with this fast-paced environment. And the only antenna in S-band, we have it here, right outside the building here, and another antenna UHF in 2 locations. But as I've covered, it's not exactly meant for operations. It's more of a backup link and an additional option. So yeah, if we had more resources, it would be an easier job. But sort of the topic of the mission is to be kind of on the edge, improving, iterating, and yeah, for good or for the bad, for bad, it keeps you on the edge of the seat most of the time.
Great insight. Yeah, thank you very much. It is really interesting to see the different missions and the different operational concepts. If you go for manned spacecraft, so you have like the ISS, you have different constraints there. Of course, you have more personnel there and resources. On one hand, on the other hand, it is really stressy if something goes wrong. I can report about that because you have astronauts on board and you have to react 24/7. And on the other hand, you have a different kind of operational concepts and aspects. If you go only for a launch aspects, like if you go for rockets, because we have also some other missions concerned on that, and so there you are. Well, you have a different approach because it is launch. It takes some minutes mostly, and then either you're in the right orbit or you lost. It's another approach again. So it's really interesting and it's amazing. Thank you very much for this great presentation. It was very interesting for me to see this side and also this frequency you were talking about. Of course, we were more stressed on well, in another way of the ISS, and if there was some problem or I don't know on what water pump or whatever. So yeah, it was really not nice to have a stress meeting and decide within minutes what to do and so on. But there was a kind of not this frequency you were talking about, because we had longer periods, we had signals, and we were not well so often in loss of signal, and we had to react. On one hand, on the other hand, we have terabytes of data we had to analyze. Well. Each day. So it's really great. Thank you very much that you found time to give us this presentation, and I hope it will inspire some of the young people. It will be great if you could provide us the presentation and of course the also this the video of the recording of this presentation. That will be really great, and so I will then distribute at least the presentation to the participants. Thank you, Martin, and all the best. I informed Søren Pike about your plans, but he was unfortunately not able to join. I was in a chat with him, and I will forward him the presentation, of course. And he also answered that one other student, Leah, was also using this some part of the system. So
I believe
he's
she was
involved.
I believe she was an intern, not too far away, like not to yeah, she was like a year or year and a half ago. I think
okay,
so.
great.
I believe she was from the first pilot run of some other project, but yeah, I think she contributed somehow.
Yes, very good.
So if you have any more questions, I'm also open. So
one thing I just thought about: how big is the team running OPSAT?
good
Like,
question.
how many?
So how many people? Yeah. So again, it's kind of interesting how the team is laid out, because it's kind of low resources in a way. Yeah. So as Professor Matewska mentioned, like some of the mission get huge resources, so it could be like dozens of people. Yeah, and they work in shift as you suggested. Yeah, they sort of like split the time between the everything, and yeah, they have a proper structure behind it. Here is much less toned down. So I think at the moment we have 3 contractors working full time on it, and then there is a constant flow of interns over time. So I was just before me, there was an intern. I started in August, and I worked for 6 months, and then after me there's going to be another intern, which I'm going to hand over to. Just a month ago, my friend finished his internship. There's actually no one to replace him, but yeah, there's always a 1 or 2 interns which keep it fresh. Yeah, so bring new ideas, fix old problems, move the needle forward. You know, it's kind of just keeping it fresh and changing. But there is also first of all, Dave Evans, the manager of the project. He's like the overall mentor, and he knows the most about it. He lived through the entire thing since the conception. He organized the finances behind it. So he built the project, and now he knows everything about the operations. But the daily operations are handled by some of the contractors who work here. There is at least one guy which is working for what I know the entire mission. We also are supported by some of the people that build the mission, so we also keep in touch with them. So if we need to find a solution to any particular problem, they're more or less reachable, and they can explain to us what to do about any particular case. And we have one person working overseas, actually in the United States. Hi, George. Yeah. So like together, like what, 6 people, I think.
That's on the one hand a small team, and on the other hand quite a large team. I mean, if you think about it, that we in our second pilot run we're what, 10 in the end, and yeah.
Like maybe if we had enough resources, we could actually launch the satellites, and operate it. Yeah. So yeah, in our group project last year, we were designing a satellite, not very much different from this one we described. I think it was doing it had another scientific purpose, but yeah, there was 10 of us doing it, and if we had a similar background, if we had more resources, more time, more effort, it could, like within 10 years, it could be an actual mission. So I'm not actually clear what you are doing in this year's group project, interdisciplinary project. But if it's a free unit CubeSat by any chance, like think that if we had about 2 million euros and 10 years, you could launch it maybe, possibly.
Machi, do you by chance remember how many people we set aside in our planning for the operation of the satellite?
I don't remember. It was like too long term,
Yeah.
5 years, something like that. Yeah. But that was a low pace. Yeah, that was just like once a month we get, and we were using UHF radio, which was like 10 kilobits per second, and like downlink it would be like just drops. Yeah, it's like we get some data. We get some data.
Yeah.
But that's funny you mentioned that. A really inspiring moment. About 2 months ago, we were visited by as a team from Dublin, AirSat-1 mission team, and they got. We also throughout the last 6 months we get an opportunity to give some courses to external people about operations led by Dave Evans. And one of the teams we gave, one of the more experienced members of the team gave a presentation to was the Dublin team, and they actually launched a satellite which was almost exactly like the one we designed. It was like 1.5 CubeSat units, but it had a similar testing some materials, a similar scientific purpose, and they have really similar communications layouts. They have UHF, VHF radio with a really small data rate, and they're just getting. So they wanna see long-term degradation of some material like we did, and basically they're radio will be fine, and I can imagine their operations is just like maybe once a week. You get some data, you analyze it, but what matters is the long-term perspective of a few years. Yeah, you don't really need to work hard to keep the system running, and if it fails, like it fails sadly because like we don't have much choice or much ability to fix it. Yeah.
Well, another thing I just remembered. Why did you doom space?
Doom space, yeah. This is when I joined. When I joined and I saw the chess experiment, I was like, "Cool, we got chess running on this thing." But it is a computer. It runs Linux. Doesn't run Doom. Doom is one of the first computers games that ever were ever built by John Romero. Like a 2D shooter game, you might know it. You shoot monsters, you move left and right and forward. And this is the simplest game you can possibly run in space. For me, it just ended on the idea, but I pitched it to some of the team members. And then about November, there's been a great presentation made by a guy called Olaruf. And he showed that he can run Doom in a really nice way, which is totally compatible with OPSAT. So we ran the logic of the game on board. And technically, OPSAT was probably the first satellite to run Doom in space. I mean, perfect. I'm so glad I was part of it. It's like world event for me.
I saw your LinkedIn post that was like, wait, what did you do?
Perfect. I did the simplest thing. I only scheduled the experiment to run. They did all the great job. All thanks to them. I just took their code, I put it on OPSAT, I ran it, and I'm like, hey, doing space. So yeah, perfect. This is the pinnacle of space of computer science humor.
Okay, do we have any other questions from the other participants?
So thank you very much for this meeting. It was great talking with you, and yeah, see you in space, I guess.
Yep.
Thank you. Bye bye.